Hi friends, so in this session we are going to see the forced vibration due to rotating unbalance. Okay, so consider one system. Consider one system of mass m. So I am drawing that system. Just wait. So this is the support, this is the spring, damper, mass. So we have one spring mass damper system. Now in this mass, suppose there is a rotating unbalance. Means you can consider one crank which is rotating. So suppose this is the crank which is rotating with angular velocity omega, and the mass of this crank is m0 and the radius is, you can select e. So small e is the radius of this rotating unbalance. So you can see normally in any vibrating system, normally we have mass, spring, spring, damper. Now in this system there is one rotating unbalance. Now why this is rotating unbalance? Because this crank is rotating, and with the rotation of this crank, this mass will experience the centrifugal force, and the centrifugal force is given by m0 omega square e, that is m omega square r. Here mass is m0, speed is omega, and its radius that we have taken is e. So the force acting on this system is m0 omega square e. Now consider the displacement of this mass is x. Displacement of this mass is x. Now because of this displacement we can write the differential equation. Now before writing the differential equation, just remember that the total mass m0 contains this the total mass m contains this m0. So sum of the part of this m is m0. Okay, now I'll write the differential equation for this system. Now how to write this differential equation? If I consider only the mass, then by removing this rotating mass m0, then the total mass of the system becomes m minus m0. So the mass of system I have considered m minus m0, means without this rotating unbalance. Then m, the formula is m x double dot. So m d2x by dt square. Okay, for this system m x double dot. Now plus here in the initial stage I have removed this m0. Now consider this m0. So for m0 how we can write? M d2x by dt square. D2x by dt square. Now here we can see we have taken the double differentiation of displacement. So the displacement of this mass is x. So displacement of m0. Displacement of m0, how we can write? This x displacement along with this vertical displacement. X along with this vertical displacement. So how to consider this vertical displacement? So for that we will have to resolve this one. Okay, suppose this angle is theta, then this vertical will become sine. So the vertical will become sine. So we will have to take this radius, vertical component of this radius. So this will become e sine omega t. Okay, so the displacement, vertical displacement of this one is e sine omega t. Or you can draw the triangle. So make a small triangle here. This one is e, this angle is theta, and you want this vertical distance of this e. So take sine theta for this term. So this sin theta will be considered a divided by e, so a will become e sin theta, and theta is nothing but omega t. So the vertical displacement of this mass is e sin omega t. So actual total displacement of this mass is, along with the total mass, it will displace through x distance, and because of the rotation it is e sin omega t. So the total displacement will be x plus e sin omega t. Okay, so I have taken, see, displacement of this mass by subtracting the m naught, and then I have taken only for m naught. So it is m x double dot, here m x double dot, here x is x plus e sin omega t. So the total term is m x double dot for both the masses plus kx plus cx dot is equal to 0. So this is the normal differential equation normally we write for any vibrating system, and that equation is nothing but, here I'll write mx double dot plus cx dot plus kx is equal to 0. So here you can see mx dot double dot, this is the mx double dot without rotating unbalance, here mx double dot for rotating unbalance. So this total mx double dot will be this total term, then cx dot plus kx is equal to 0. So this is the differential equation. Now modify this differential equation. So I'll multiply this x double dot inside, so this will become mx double dot minus m naught x double dot plus, here again take individual differentiation, so this term will become m naught d2x by dt square, that is x double dot plus m naught, take the second term d2x by dt square for second term e sin omega t plus kx plus cx dot is equal to 0. Okay, so here see, this minus and this plus term will be cancelled, and this will remain as mx double dot plus m naught. Now take the differentiation of this term 2 times. So I'll write this differentiation here. What is the differentiation? E sin omega t, we will have to take the differentiation. So the first differentiation will be, the first differentiation, E is the constant, differentiation of cos sin is cos omega t, and differentiation of omega t is omega. And the second differentiation, E is constant, omega is constant, differentiation of cos is minus sin omega t, and for omega t it is again omega. So this term will become minus e omega square sin omega t. So directly I'll write here minus e omega square sin omega t plus kx plus cx dot is equal to 0. Now transfer this minus term on the right side. So this equation will become mx double dot plus kx plus cx dot is equal to m naught omega square e sin omega t. So this is the differential equation of vibration for the given system. Now we'll go back and I'll write the formula for the differential system that initially we have used. See, for forced vibration, the differential equation comes out as mx double dot plus cx dot plus kx is equal to f naught sin omega t, because in forced vibration we use the force f naught sin omega t, and its solution is x is equal to a2 sin omega t minus phi. Okay, and this a2 means amplitude of vibration, or you can say x. So x sin omega t. So in this solution, the amplitude of vibration that comes out is f naught by k divided by root 1 minus omega by omega n square bracket square plus 2 zeta omega by omega n bracket square. So this is the formula. Now compare this forced vibration formula with this equation. Compare. After comparing, we will get the solution. So here you can see mx double dot, cx dot plus kx. Here you can see f naught sin omega t. Here we have, instead of f naught, we have one term m naught omega square e sin omega t. Means in this equation only f naught is replaced by m naught omega square e. So I can directly write the amplitude of vibration. So solution of this equation will be having amplitude. What will be the value of amplitude? X is equal to, here f naught we will have to replace by m naught omega square e. So this will become m naught omega square e divided by k divided by root 1 minus omega by omega n square bracket square plus 2 zeta omega by omega n whole bracket square. Okay, so this will be the final answer, and this is the amplitude of vibration. Now if you want the phase lag, that phase lag, that is the phi or phase difference, you can say, that is the phi is nothing but tan inverse 2 zeta omega by omega n divided by 1 minus omega by omega n square. This is the phase difference. Okay, and the solution, instead of this we can write this solution as x is equal to x sin omega t minus phi, and this is the value of x and this is the value of phi. So this is the amplitude and this is the phase difference. So to solve this equation, I just started with the differential equation, come to a differential equation which will be very similar to the differential equation of forced vibration. So from that I have directly taken the amplitude and phase difference. Okay, and this is the derivation for forced vibration due to rotating unbalance. Thank you.